Hello, I feel a little out of place because systems architecture is where I come from. My talk is probably not going to be strictly systems architecture, so excuse me if I maybe stray off topic a little bit. And I assume people ask questions here, or is this I'm supposed to talk? You guys are going to sit quietly for the whole time. Either way, I'll work with it. I'm Quinn Jacobson. My PhD is in electrical and computer engineering from the University of Wisconsin. I've had a lot of fun over the years. I did do, I believe, the first soft core IP block for an FPGA that was commercially released back when Altera was moving to the into the Flex family of products. What I'm probably my sort of, one of my biggest accomplishments was I was the chief architect for UltraSpark 4 and 4 Plus at Sun Microsystems. So I got to lead the design for the move at Sun to multi-core for the Spark product line. And so I worked on very big computers. We had some rack mounted, but that time this was the old, servers in the middle of the data center, big standalone computers. I worked at Intel for a while, and then I went to Nokia. I went to Nokia to build a Linux phone, but Nokia decided that Symbian was such a great operating system that why would they abandon it? And so what I did instead was, this was about the time that GPS was starting to come out on cell phones. And so I led an effort that did one of the first crowdsourced automotive traffic apps. It was really fascinating. It was a complete departure from everything else I had done. Although I did learn something really interesting, how small the world is. So when the topographers are trying to figure out how they're going to represent road networks and how to navigate on them, they decided that instead of inventing something from scratch, they could just borrow. So it turns out if you ever, I recommend, go find a map database for road networks and open it up. It's a net list. What they do is they call highways or high-level metal, surface streets are low-level metals. They have vias. It turns out that all you're doing is routing in a net list. And so it was fascinating to discover that I was really just going to do optimizations on net lists again. We had a wonderful program. We had one of the first services that had traffic on non-highways. We only had one small problem, and that was that the executives wouldn't let us launch on either iOS or Android. And hence, we were a little less than successful than some of our competing platforms out there. And then about 4 years ago, I left to start Vibrado Technologies, which is what I'm going to talk about today. And I was at Nokia, and I was working on mobile devices. And there's really a fascinating transition when you go to mobile devices. We went from personal computers to portable computers, and something really changed when we went to mobile devices, because not only did we bring compute with us, but compute became aware of us in a way that it never was before. And so one of the really cool things that happens here is we have a device that only is connected to the digital world, but it's aware of the physical world with lots of sensors. There's motion sensors, there's cameras. All these sensors make this device fundamentally different, and our interactions with it fundamentally different. But what I saw when I was at Nokia was there's some really cool things you can do in terms of trying to understand what a person is doing by looking at the sensors on the phone. And we do this today. Anyone who's using their health apps know that the phone can sit in your pocket and determine how many steps you probably took during the day. But if you're looking from a single point source on the body, you kind of have to approximate the person as sort of a perfect sphere, sort of like your classic intro to physics, right? We're going to model the person as a perfect sphere, and we're going to see how they're bouncing. So we took a step back and said, what would we like wearables to be? Not, what can we do with a phone or with an app, but if we're going to start over, what would we really want from a wearable technology? Because I feel it's inevitable that we're going to have networks of sensors in our clothing. Sensors are cheap. We're in our pocket. The logical next place for them to do is to be integrated into our clothing. So we looked out and said, well, there's a lot you could do. If you could actually observe what someone is doing and how they're doing it and actually get a holistic picture, there's this whole range you open up. Everyone probably remembers in The Matrix when Keanu Reeves gets karate downloaded, right? 10 seconds, he plugs in, and now I know karate. We can't quite do that, but if you had clothing that could watch how you move and give you real-time feedback, it could teach you stuff much more efficiently than you could learn it on your own or watching a video or even working with a coach. So we can learn motor skills more efficiently and effectively. You can receive personalized fitness to walk you through. As we see an aging population, keeping fit's one thing, keeping mobile as you get old, figuring out how to adapt your gait to optimize. All these opportunities here for technology to really become much more aware of us and help us be the best that we can be with our physical limitations and abilities. Of course, you get injured, so then you've got physical therapy to go through. And then we have this whole domain of occupational safety where people are working, lifting heavy things. There's no reason that we shouldn't have smart garments that can detect that you're about to do something really dumb and tell you to stop. And underlying this, when we took a step back and looked at this problem, we said the whole key comes down to being able to to focus on the quality and not just the quantity of motion. And it all comes back to creating a feedback loop. The only way you affect someone's behavior is through feedback. And so what you want is a system that in real time will observe what you're doing, will analyze what you're doing, and give you feedback in the moment. And that way you produce a feedback loop that's very efficient, and that way you can help people improve what they're doing, learn correctly, and avoid injuries. So, any questions or comments? It's a quiet crowd here. If we can do this, there's this huge opportunity out there, right? If we can actually build smart clothing that will be aware of us and help us, there's all the sports domains, fitness. People are spending huge amounts of money really inefficiently. We're paying to go to a class where in a 90-minute class, the instructors may be looking at us for 3 minutes to evaluate our form. The other 87 minutes, we're simply doing bad form with no feedback on it. Or, if you look at senior health, we spend $34 billion in this country on direct medical costs from seniors falling. We spend tens of billions on physical therapy, and there is a massive shortage of physical therapists because there's more demand with an aging population and our unhealthy lifestyles for physical therapy than there are physical therapists to serve that demand. And then if you look at occupational safety, $50 billion spent on workers' compensation for workers injuring themselves on the job.
Quick question, your 13 billion is just civilians? Or include the military rehab?
For that, for which one? The
13 billion, physical therapy.
That's just for ACL tears. If you look at physical therapy as a whole in this country, it's about a $27 billion and that's just the cost. That's just for knees. Is $13 billion.
But the 27 would include military.
It's hard. The VA is really hard to get exact numbers from, so it's probably larger. And we do know there's a shortage there where actually people would consume much more physical therapy if it was available.
Yes, absolutely.
And so there's this huge thing, and it's really not that hard. I mean, physical therapy is about observing how someone's moving, guiding them to do an exercise, tracking their range of motion over time. I mean, computers are really good at this. This is what we do. We observe, we analyze, we can guide.
Anything for swimming? Anything for swimming?
Swimming? Well, I'll talk about specific products, but every sport has a motion. And when I go around and talk, and I'll show you one of our products, everyone's always got their favorite sport, right? And I like swimming. Swimming is really a form-centric sport. I was a swimmer. That's what I lettered in high school. And so, yeah, swimming is a perfect example. If you watch someone swim, I have 2 teenage boys who both competitively swim. It's all about form. You can have a lot of strength, but if you don't get the proper form, you don't get the performance. And there's really no good way to do this. What I end up doing is I lay in the bottom of the pool with a video camera and video them swimming above me, and then I have to swim to the side of the pool. We look at the video. It's really cumbersome. Same thing in every sport. I have people come up to me like, well, what about bowling? What about lacrosse? What about golf, tennis? Every sport has a set of skills. All we need to do is take the set of skills, map them out, and then guide people to do them correctly.
Or shock them when they don't do them correctly.
The most requested feature, shock feedback.
But instructed
Or
by
what's buzzing? Buzzing.
Buzzing's easier, but the shock is highly requested. It's like usually it takes about when we're talking to customers, it's usually about 30 seconds in. Like, well, then can it shock them?
You sell those to prisons too?
Well, there's a bunch of problems. We avoid shock as a feedback mechanism.
I think you might have some issues with the nervous system at some point.
There's a lot of problems there. Although if you really want to get to the extreme end of this, some really interesting stuff is you look to e-stim to actually stimulate muscles. So taking a step back, if you really want to get into it, there's a huge opportunity that someone wants to talk to me afterwards. We can talk about how, as you're watching someone's motion, a lot of people struggle because they're not firing the muscles in the correct sequence. And one of the things we can potentially do is, as you're doing a motion, we can provide very low e-stim to help teach your body which muscle they should be firing. And so the way e-stim works is if you apply a small current to a muscle, it actually will hurt slightly if you don't go with it. So if I want you to contract your bicep, I can actually send a small current to it, which will only tingle if you don't flex it when I tell you to. And so there's actually ways that, if you want to look at it, we can really take shocking to a whole nother level, but that's kind of beyond maybe the scope of this conversation. But there's actually a huge opportunity there. Early wearables. We have wearables. They're everywhere. And they're not bad. They're just not that useful. And let me tell you why I think that is. There's an information gap. So there's an amount of information that we can get from a device, okay? And what are you doing? How well are you doing it? What should you do differently? What we're trying to build up to is what you want as a person is some sort of actionable insight. What can I do differently? How can I live healthier? How can I swing my golf club better? It's all about what can I do to be better? How can I get over this injury quicker? How can I regain my mobility? The problem is that if we look at most wearables today, say a general fitness band, it's measuring some little bit of information here. Now, the information it's measuring does not have any actionable insight in it. So, well, we have to close that. So we have the system infer what's going on. Well, that's very error prone. If I have very little information and I'm trying to guess what you're doing, anyone who owns a fitness tracker knows this. There are some days like you'll leave it on top of the washing machine and suddenly you've done done a marathon. There's other day you wear it all day and somehow you didn't do any steps. They're inferring what's going on and sometimes they get it wrong. And so how we close that? Well, we infer. It's error prone. We get better. The better the algorithms, the less errors it produces. But then all you can get to is some point that you're still left to interpretation by the user. And so this puts a burden on the user. I give you a graph. I give you some information, and then you have to figure out how does that apply to me and make my life better. Because you only get value from something when it can actually change what you're going to do. Information theory. If I'm going to do the same thing, then I haven't actually gained any information from the system. Now, we can get slightly better if you look at sort of state-of-the-art in some of these sports-specific wearables. They do slightly better. It's not because they're actually any better. It's just because the universe is smaller around them. So if I know I'm on the end of your golf club, then I know that you're probably not on a bus or on a bicycle. I know that you're swinging. And so it's not that these wearables are any better. It's simply that they have reduced the universe to a point that they have a better chance of getting correctly what you're doing, and therefore there's a slightly smaller information gap. But what you'll still see if you look out there today is that all of the devices on the market today still put a huge burden on the user. The information they're giving you is a graph of data or some arbitrary measurement of data that doesn't tell you what to do differently. It tells you some metric of what you did. You left the plane of your swing by so many degrees, or you hit with so much speed. Well, that's interesting. It's maybe a number I can even optimize for, but it doesn't tell me how to optimize for it. So at the end of the day now, I still don't know what to do differently. And then the only thing I have left is trial and error. So with most of today's solutions, all I'm trying to do is they'll give me some metric, and then I'll just sort of try a little bit of this, a little bit of that, and well, that looks a little bit better. I get a better number. But what we need to do, if we're going to actually produce wearables that people are going to love and are going to change our lives, is fundamentally close this gap so that with high confidence, we can tell someone an action of what to do differently in their life, and we can tell it in a way that leaves very little burden on the user to interpret. And so basically we want to recreate, if I had the world's best coach or world's best personal trainer or world's best physical therapist staying next to me, what would they tell me? And can we, with a digital system, give you that same answer? In which case, then I think we've provided a service that's highly valuable and is really a game changer. So how do we do that? Well, we've got to solve, there's sort of, the way I broke it, and you can slice any way you like, but the way I look at this is there's three pieces of this. We've got to figure out how to observe enough data so that you can really know, what someone's doing. And that means that if you're trying to help someone be a better runner, being on their wrist is not very useful. Yeah, I can give you roughly probably how many steps you take because there is some repetitive patterns in there, but it's not really going to help you be a better runner. Once we get a lot more data, we have to be able to do much more accurate analysis of that data. We have to think of how to interpret that data in a way that's very efficient. And we've got to make that data easier for the user. And one of the really sort of interesting things here, if you go back to my information gap here, is the more data the system can actually learn, the simpler of commands it can give to the user. Because it actually knows what's going on. It puts less burden on the user to interpret and understand. So the more complete picture that our technology can build from on what someone is doing, the more we can give them a simple, actionable thing where it doesn't take a lot of thinking by the end user to understand what they're supposed to do. They don't need to be a domain expert themselves. So let's take these sort of one at a time. I'm an engineer. What do? You slice a problem into pieces. You solve them one at a time. The first, how do you get more data? Well, more data is actually really simple, right? If I want more data, I need more sensors. Now, what we've been working on is systems where we actually build garments that have lots of sensors in them. Sensors are cheap. They're fairly, thanks to the cell phone industry, MEMS sensors are really good and really cheap. So every one of our cell phones has a little MEMS gyros, MEMS accelerometers. Those components are wonderful. Now there's some challenges. If I'm going to put a bunch of those into your clothing, I need to be able to synchronize them. And this is actually quite a challenge because a lot of what people have looked at in terms of how they're going to network together sensors on the body don't take into account synchronization real well. Even if I have the bandwidth to move all the data from all the sensors, if I can't synchronize them in time, well, if I know where one body part is at time t1, and I know where another body part is at time t2, if I model a joint in between, how accurately I know that joint angle is a function of how close I know t1 versus t2. It seems very simple, but if you look at what a lot of people are doing in the wearable space, they're completely ignoring this. Another problem is calibration across sensors. MEMS sensors are wonderful. They're surprisingly accurate for how small and cheap and power efficient they are, but they're not absolutely that accurate. We have a lot, you have a strap-down gyro, so inherently strap-down gyros have drift problems. So we don't, when we build these little cell phones, if you look at the gyroscopes in them, you think of gyroscopes as these nice spinning things and a gimbal, and they can move around, so you always know where one direction is. That's not how we actually build them. They're a strap-down gyro. We know how fast you're rotating. We don't know where you absolutely are, and we just integrate how fast you're rotating over time, which causes just compound errors over time. So we gotta calibrate across them. Calibrating one sensor is hard. Calibrating across lots of sensors is harder. Especially if you look at sensors, if I'm a sensor, I want to think of trying to keep your orientation in space. If I'm a sensor, in terms of what, if you think of your airplane terminology, my pitch is, well, I can correct if my gyros go bad on pitch real easily because I can always look where gravity is. Gravity is always there in the background. I have an accelerometer. I can see down. So I can correct for pitch. I can correct for roll real well for my gyros. What I can't correct for is yaw. So if the gyro drifts a little bit to the left or a little bit to the right, I don't know that happened. I have no way to correct for that unless I get real creative. Now, if I'm one sensor and I drift a little bit to the left, a little bit to the right, that's okay. But if I'm modeling a joint and I'm two sensors and they drift independently, suddenly I have a compounding problem. So we have to solve the problem of how to calibrate across sensor nodes. You got to, of course, have enough bandwidth to talk to all your sensors. As in all of computer architecture and computer systems, ultimately power is always going to be your limiting factor some way or another. So if I put lots of little sensors out there, somehow I got to get power to them. I either have to have a power distribution where I run wires through your clothing, or I have to put lots of distributed power and put lots of little power reservoirs out in the system.
Are you more interested in collecting spatial data as opposed to, say, something like physiological data, temperature, salt, galvanic skin response, which are sort of the traditional?
We're looking at the harder problem of biomechanical data, of motion. There's lots.
There's spatial data then.
We're working on spatial data. It all correlates, right? Because really we're trying to build a holistic model of the human. And there's a lot of really good work going on in terms of how to do the other physiology data. We can talk about that if you want, but what I'm mostly going to talk about right now will be the spatial motion data. And if you're going to put lots of little sensors out there in the world, and you've ever been to a Computer Architecture 101 class, you know you should program as a distributed system, just because you should. And there's lots of efficiencies if you do it right. I'll put a little plug for a technology here. When you look at wearables and putting lots of wiring up humans, you spend a lot of time worrying about wires. Amazing cables. And you think that wires, this must be a technology that's, what can you do interesting in wires? There's a company called Minnesota Wire. They have a really cool wire. It's called iStretch. They put an elastic core and they coil the conductor down them. What it gives you is a wire that's extremely flexible. It stretches. You can actually stretch your cables, and they have basically an infinite bend cycle on them. Because of the geometry of that, when you bend a coil, you don't actually put a crink in any of the conductors. You produce a cable that has a infinite, nearly infinite bend cycle. And I say nearly infinite, actually, I've worked a lot with these guys. A number of years ago, when they first started making this for the military, they put the standard test in where they're doing bend cycle testing. 2 weeks ago, they took down the machine after a few years and millions of cycles because they couldn't justify the lab space anymore. They had 0 breaks. So they don't know. They don't know what the bend cycle of this wire is. But if you're ever in the space of wires, really fun wires to play with.
What's the size of it?
It comes in they make it in all different conductors, gauges.
Sure. But the kind that you would use?
So the kind we're using is very small. We're using 32 gauge conductors. We don't need a lot. They do big conductors. If you're going to lay big cables down, they can do big conductors. We're using really fine conductors. The other thing you got to worry about if you're trying to model how people are moving is actually building clothing for people. And honestly, when I started Vibrado almost 4 years ago, I was really worried about my electronics. I knew I had some challenges there, but I thought I knew what to do. And I kind of like, well, and we'll have to build some clothing to put them in. Turns out garments are actually probably harder than electronics. So there's one thing to take away from this. I guess the thing is, whatever you know is you probably can solve this. What you don't know is going to bite you. Clothing's hard. We need the sensors to move with the body if you're going to model how people move. And actually, that means the clothing has to fit well. Not only that, but clothing's actually not designed to move with you. It's actually designed to shear. So because you don't want it to sort of restrict you. So actually, when you look at clothing, in almost all cases, clothing is actually made to not track how you move, but actually give you some degree of motion within the clothing, which then completely defeats the purpose of trying to use clothing to observe how you're moving. And people really care what it looks like, so you can't just sort of, you can strap a bunch of stuff, but not if you want to actually be able to use it in the real world. Washing cycles are brutal if you're building electronics. And although you can always put the do not dry on the tag, you can't guarantee people don't put stuff in the dryer. Working with the garment industry is very hard. It's not an industry that has really moved into the 21st century at all. And actually, it's a bureaucratic nightmare, actually. To manufacture a garment legally in the state of California, you have to go through a whole process to become a licensed garment manufacturer. Even if you're going to produce one, if you're going to sell one garment in California, technically you have to go through this huge bureaucratic nightmare. And so we had to go become a licensed garment manufacturer. There's a whole set of law just for garment manufacturers. It goes back, I think, to the fact that garment manufacturers have historically so violated worker rights that you have to then go through this whole process to verify that you're not going to exploit workers. Even if you're making extremely high-end garments with electronics in it, they still think you're...
So you're saying that you need these type of sensors. Does it mean that you need to develop them, or do you already have these type of sensors? Is the technology there or not yet? That was one question. Another one is that about California, there are some restrictions about like hazardous material. Is that also a concern in using the sensor with specific material in the clothing in California?
No, the hazard material is not the problem. It's simply that California goes back to really archaic rules when it comes to garment manufacturing. Building the sensors are not hard. Every cell phone has a chip that's about 3 millimeters by 3 millimeters, which gives you all the spatial data you'll ever need. And so if you're trying to build motion capture systems, we actually have the building blocks quite readily available.
Like in terms of, for example, stretchable fabrics that are sensors, like is the technology there, like reliable, something that you can use that has those properties that you're...
So it's not. If you try to look at it, and we looked at this, everyone's promised to give me textiles with wires woven in them. And textiles with wires woven in them have been, you know, ready next year for, like many other things, next year you'll have them, and we've been told that for 10 years or more. We know how to put wires into textiles. You can weave wires into textiles. Doing that in a way that can survive real-world wash cycles and can deal with what we really need wires to behave like is not practical. So we gave up. We spent a lot of time trying to figure out how we were going to go get textiles with wires woven in them and said, well, I'm just going to run a cable because, honestly, I want to retire before I'm going to get the garment industry to give me a cloth I like. It's coming. They're getting better. I'm seeing some of the embedded conductors that are showing some promise, but no one's ready for commercial production of textile with embedded conductor. Moving on, so collecting data, we know how to, we have the sensors, the building blocks are there, we know how to build networks of them, we can put them into clothing. What do we do with the data? One of the things, when we looked at this problem, we focused on the fact that we didn't want to take our data and run pattern matching on it, on sensor data, which is sort of the classic way that most people address this problem. I have a bunch of sensors, I have some really good machine learning algorithms, I'll put the two together and my job will be done. What we found is it's actually much more efficient and much more powerful to take your sensor data and turn it into a biomechanical model. So don't try to look at raw sensor readings, but take your sensor data and model the human body. You get all the benefits of the fact that we know how human bodies move. There's a lot you can do when you're trying to model a human body that just looking at sensor data throws away. It also is very much more robust. If I'm trying to do pattern matching, I have to look at every possible way I could swing a tennis racket. Whereas if I'm trying to build a model if I build a model of an arm swinging, I know the natural expected variations in that. And we can argue about this, but it's actually substantially computationally more efficient to model biomechanics than it is to scale pattern matching algorithms to the scale you need to solve these problems. And the other really important thing is, as we're looking at systems, by running biomechanical models that are human understandable, we can produce user experiences that are much more useful and much more compelling for both the end user and the domain expert. And so if you're trying to show someone what their sensor data was when they did it well and they did it bad, that's sort of nonsense to the average person. But if you build a biomechanical model, you can say, you know, get your arm up, bring your elbow in, move your wrist this way. It produces a way to communicate to the people. They understand. People understand stick figure models. They can manipulate stick figure models. An expert could take a stick figure model and say, I want you to do this. I want you to take your arm and I want you to swing it like this, or whatever it is. And if you do your like that, you can say, you swung your arm like this, and I want you to swing your arm like that. And people understand that. And so building systems that people can interact with and where we can close the information gap to provide people actionable input, it's really important that we build our systems to work in the biomechanical domain that people understand. I think I covered that. And the other important thing is providing feedback to people that's useful. So if you want to provide useful feedback to people, we got to give them information in a way that that gives feedback that's accurate, timely, and meaningful. So we have to give. It has to be objective. It has to be precise. It has to be repeatable. People have a very low tolerance. If you ever tell them something wrong, they no longer trust you. So you have to always give them the right answer. You have to be accurate. You have to be timely. So if I go, today, what do you do if you want to learn to do something? Well, there's always a videotape yourself doing it and then review the video. Well, one, no one actually goes back and watches the video. And two, if you do, it's too late. You see what you did wrong, but now you're no longer doing it, so you can't build muscle memory for the correct way. And it has to be easy to understand, easy to implement. So it's going to be something that I tell you it's how a person would tell you to do it so you can interpret it. So we spent a lot of time working on on-body feedback. How do we communicate to people? How do we convey information to them? Well, if you do something good, you just want to give them some sort of nice congratulatory tones. If you do it bad, well, if you can actually light up arrows on their body, in this case, I want her to get her elbow in, I want her to get her hand forward. Just draw an arrow on the human body. That's something that people can understand. Look at your arm. Oh, you want me like this. That's about as simple, as straightforward as you can get. We don't want you to interpret it. We don't want to try to give you some angles where we want to say, get your arm in. So, what have I been doing? We spent the past few years developing a modular software architecture that does this, and the hardware. We had to build the hardware, of course, but the real interesting stuff was the software algorithms to take any biomechanical data, interpret that data, and put it into a model that is a stick figure model where we actually can overlay other data. We can overlay muscle data. We can overlay other biometrical data. And then building algorithms that can very quickly run on that model and give you instant feedback on what to do, how to behave. And so we've built full body suits. I can do the stick figure moving. But those actually weren't very useful. We were looking for something a little bit more scaled down as our first product. So our first product actually is from Vibrado, is a shooting sleeve for basketball players. So you slide it on just like a player would slide on any compression shooting sleeve. I have 3 sensors here that are tracking my hand, my forearm, and my upper arm in space. So as I'm wearing this, the computer sees a little stick figure arm moving in space. So I can dribble and I can pass, and it's just watching me. And if I then go up to shoot a basketball, it will, if I turn on so you can hear me. If I go up to shoot a basketball, and I'm not sure if the mic will pick this up. If I shoot a basketball well, it'll give me positive feedback. I see some nice sparkling lights. I get told, great job, repeat that. Now, if I break form and I do a basketball shot, it's going to recognize I broke form. It's going to give me feedback what to do differently. So if I shoot and say I don't snap my wrist, it's going to scold me, and it's going to tell me to get my wrist snapped more. If my elbow comes out, common mistake players make, you'll see that I get scolded, I get told to bring my elbow in. If I shoot flat, I get told to bring my arm up. We can go on and on and on. There's 50-some things that can break down on my shot. But fundamentally what we're trying to do is take it and give you very simple, immediately actionable feedback where I can improve my form. Now, you can say I'm not a basketball player. Well, that's fine. What we're trying to show is the building block of how that can be applied then to any sport or to physical therapy. The same principles apply. So let's see. A little bit more about this. You can see what we've done in our implementation, our nice stretchy wires. We spent a long time looking for more graceful things. We went with Velcro. We have a garment, it has Velcro on it. We have electronics, they have Velcro on them. You can mate them and use them. And then you can throw this in the washing machine and not throw this in the dryer. So this is something that's being used. Actually, we have customers in the NBA and NCAA that are using this. I'm not allowed to. One of the frustrating things I have is that I can't show you the data. We've got some really cool data that shows we actually have one team where we've got about half the players on the team chose to use it this year, and about half the players didn't. And so the players that are using it have seen their free throws go up this year compared to last year from 6 to 33% increase in the free throw percentage. And the players who chose to not use it have seen at most a 2% improvement. Instant feedback on form is amazingly powerful. We've seen players who are veteran NBA players. These are people who've shot, I can't even count how many shots they've probably done in their life. And I'll have a shooting coach that says, I've been working with this guy for years. I can't get him to change his form. When you put something on their arm that gives them immediate feedback like this, and people naturally, when you hear a good tone, you naturally want to repeat it. If you're a bad tone, you naturally adjust. We've gotten people who are veteran players who in 1 hour will actually make a very noticeable change in their biomechanics.
If you're saying it has this much of a difference, have you thought about, like, are there going to be any rules against it? Is it going to be cheating to use this kind of product in a professional environment?
We're using it to help your practice. We're not going to let you use it in the game, probably.
But, like, for example, in the Olympics, let's say that one team has access to this product, but the other ones can't afford it.
It's an excellent question. I don't know. Technology is usually ahead of those issues. I mean, traditionally today, I would say no. I mean, there's so many training aids that teams use that it'd be hard to see that being raised. In theory, yes, I see your point, but I don't foresee that being an issue.
Just tying into the question, I think almost that could be generalized, right? The question itself could be, if you're coming from a better country, you got access to a whole lot of infrastructure that you don't have if you're in another place. So
yeah, having a better coach, having a better gym, it's hard to see that. But
this is great.
Throwing with this thing on and without this thing on, are they two different things? Like practicing with this thing on may not do wonders on the match.
So one of the key things we want a product that would completely move with you. It doesn't in no way constrains your motion. So you'll see some people have training aids that actually like mechanically try to make you do the right thing. We're not in any way mechanically constraining you. So if I wear it or don't wear it, there's a slight different tactile feel simply in the fact that I'm wearing the sleeve or not. Now, a lot of players wear sleeves anyway. And we actually do provide them a game sleeve that doesn't have the handpiece that's the exact same level of compression. So if they want just to feel the same, we can give them a garment that feels the same. But it in no way affects their actual mechanics. There may be a psychological aspect to it.
I can see a battery somewhere.
There's a battery, yes.
So surely that battery wouldn't be there in the match, right?
No, and so nor are the electronics. But the electronics actually weigh about the same as a garment. There's no substantial weight to it. I mean, they're, a little over an ounce of total weight. You look at that on a adult's arm, especially when you talk about the bulk of the weight is up here near the shoulder, there's negligible impact on the mechanics.
And I think once you remove that, the impact would be probably additive to the performance because you no longer carry.
There's a minor weight difference, but
How much of that weight is fabric?
A large fraction that's battery. Why is this big thing here? It's got really three pieces in it. One's a battery. Actually, a non-trivial part of this space is the speaker. If you don't have good audio engineers, building really small speakers don't work, so you just throw a big speaker at the problem. If I had a good speaker, if I had a good audio engineer, I could probably get about a third of this volume to go away.
What if a remote speaker?
Remote speaker? One of the key things we did when we built this, actually, there is, of course, it has Bluetooth in it. It'll connect to your phone. I can then go and set what I want my shot to be and all that. Once you configure for a player, we didn't want, when you go to play basketball, you don't have a phone with you. It doesn't make any sense to carry your phone with you or set your phone on the floor next to you.
Like a speaker on top for individual solo practice, just by yourself in the room like many players do.
You could. But from a practical standpoint, it's a lot easier just to make a standalone solution. In the back there?
Do you need to calibrate per person to use it, or does the sense link can be used by me, by curves, anything?
So the way we do it is, so if you're a beginning player, we have a portfolio of shot types based on age and skill. We can give you a shot. For more advanced players, I'm not going to go tell an NBA All-Star how to shoot a basketball. So what we do is we put in evaluate mode, we have them shoot, and we have them take 10, 12 shots, and we'll automatically construct a model of their shot. And then if they like their shot, all we're going to try to do is get them to have ever more consistency in repeating that motion. Usually, they'll actually go into our app and you can drag. So let me see if I can put this on the screen for you guys. 1 second. And we'll try this. And the AV people are going to freak out.
Now, there could be some preset security that might not allow it to play.
It should go here. I just got to let's give this one try here. There we go.
Excellent.
Okay, so when I shoot, you can see my arm in real time. I can shoot low. I can shoot high. I can shoot in the middle. And I can go to evaluate mode, evaluate my shot. The cool thing is because we're in the biomechanical space, I can have someone say, I can't get you to shoot the way I want you to shoot. I can have you shoot the best you can, and then I could, if I was a coach, go, well, that's the best you can do, but I actually want your arm to be higher or lower, somewhere else. So you can go grab the stick figure models from different perspectives and drag them around and set the mechanics you want, even if I've never observed it. So that's one of the cool things about not pattern matching, but having a biomechanical model, is I can actually give you a target I've never observed. And of course, you can get all sorts of graphs, and you can, tweak how, good a player you are, all those things you can quickly configure. And then lots of data.
Have you thought about providing a way to collect data on whether you made a shot or not, so that you can later correlate it with?
Yeah, our system actually supports, if you have an external device, it'll tell you makes or misses. The simplest being, we actually can, Some of our customers don't mind having someone push the button, but there are some of the shooting. When you practice by yourself, a lot of people use the gun. It's a rebounding machine, and those will count make misses. So if we have that input stream, we actually can tag shots as make or misses, and we can give you a breakdown of the difference between your makes and your misses.
Is the MBA itself looking for this as a data collection on statistics? Like, for example, if you put like some sort of tracking device in there, you could say this player is hitting 60% of shots from this part of the court.
The heat map of where they're making shots is being done today by the NBA, and that's there are a number of companies that provide solutions to map where shots are taken and made during games. They can't give you they can't really give you mechanics of the shot.
Right. So is this going to produce new statistics that
It could. It's actually an interesting thing going forward. Is the more you could bring more data during the game day, the more interesting you can make the announcer's position. Or even if we can't let it player wear it during the game, if the player would share his mechanics, then the announcers has something more to talk about to keep us entertained while the game is at a slow spot. And so it is there is an opportunity there to actually generate just more data on a player, which is interesting. So you can imagine how that could be used in sort of by the color commentators in a game. Or in theory, in the future, you could see real-time data in terms of how players are doing during the game.
What would be the maximum number of parameters you can put into these sensors to detect?
The maximum number of parameters. I'm showing 4 right now. We measure 50-some different parameters of a shot. We actually measure 7 if you count the timing sequencing events. Any of those can then be selected to be what a player works on. Some players will go in, and I can go to those parameters I have, say, arm height, and I can say I don't want that. Turn that off. I don't want you to look at my arm height. I go turn something else on. So we have found that a player can't cognitively deal with really more than 3 or 4 at a time. There's just for them, and so actually what we're looking at going forward is more auto selection, where instead of us having sort of a static set that you're looking at a given point in time, how do we have it that over time we suggest, okay, you've got that nailed, let's remove that and substitute this more subtle metric in, and over time give you ever more targeted metrics. The problem is that the cognitive load on the user to understand, oh, there's something else being measured and I'm supposed to get feedback on it, is quite challenging. So the limitation is how do you communicate to the player?
So do you allow some of these parameters for the display to be fixed by the player and some be auto-learning?
So right now we do it by the player. Right now, a lot of our system is built on explicitly either the player or the players we're working with have really good coaches. And so it's really actually the coaches usually who are doing it. What we're working on as we're working with these elite players is building the learning so that then when we move to a mass market, to a person who doesn't have it, that they'll get the benefit of that without needing that expert there. And so that we can then auto-suggest everything. And so that's what we're working on now, is taking the data on how elite players, and we're working with players from NBA down to high school and even middle school and elementary players who are some of the best, understand how they're shooting so we can then build a system so that everyone can have the benefit of a great coach, even if they don't have one. And the cool thing about it is, if you're out with your kid and your kid's shooting in the driveway and he does something and you don't know a thing about basketball, you can look at your phone and say, bring your elbow in. And now you're actually telling your son, your kid, your daughter something useful, even if you don't even know what it means.
How much does it cost?
How much does it cost? We don't, it's not really, it doesn't actually make sense because we actually sell it as a service, not as a product. So to our current users, we're selling this as a service that is part of a coaching service. So we actually work with coaches and trainers and personal shot coaches. And so our current clientele is not actually buying a thing. They're paying for a service of which this is helping it be a better service. At the end of the day, a consumer price point, you're looking at a couple $100.
You mentioned these sensors are off the shelf, MEMS kind of technology from cell phones, things, but how sophisticated are they? How many degrees of freedom do you have? Like XYZ accelerometers, angular X, angular Y, angular Z?
Yep. We're using 6. We started out with 9. We started out with 3-axis accelerometer, 3-axis gyro, 3-axis magnetometer, and threw out the magnetometer because they're worthless. And figured out how to deal with yaw drift in other ways and relying on magnetometer because anyone else ever play with magnetometers, just stay away from it. If you ever use your cell phone, you'll notice it doesn't really know what direction you're facing until you actually move something and it can't see that. So you're using standard commodity 6-axis.
And what kind of frequency range can you get?
We can sample, we run for a basketball shot in 150 hertz integration rate. As we're looking at some of the other sports, we have to crank that up a little bit, depending on the motion, speed of the motion.
What can the sensor do?
The sensor for like accelerometers can go up to about 1,000 hertz, which for most human motion is okay. We are finding that some human motion is too much for the MEMS sensors. Look at a professional pitcher. The rates that they're moving, a professional pitcher, actually no MEMS sensor on the market today can handle.
How about skiing? Ski racing?
Ski racing you can do. Yeah, full body suit would be great for ski racers, help them keep their top form.
I would assume that the ideal form for a shot depends on how far you are from the hoop. So do you also keep track of the position on the court and adjust accordingly, or?
Yes. So if I'm out practicing, I can hit. Free throws. Warm up. Oh, actually, I have it turned off. If you give me 1 second. We let players select different shot profiles. Warm up. Free throws. Warm up. Oop, oh, I don't have connectivity, so I can't go to server and turn on. We let you turn on 2s, 3s, so you can just tap the button if you're going to go shoot a 2 or shoot a 3 or shoot a layup. We have you, if you're using a rebounding machine that actually tells us where it's tossing the ball, we can, or if we have other sensors in the room, we can use those to auto-select that for you. But it's important
Intended,
because
like you're staying in one place mostly and doing like repetitive.
most practice, someone's working on a shot type for a period of time. And they are different. The mechanics, there are a lot of similarities, but when you shoot a three-pointer, there are fundamentally different mechanics. Interesting thing, if you look at it, if you start looking at biomechanics, Steph Curry's got really fascinating mechanics on his three-pointer. He does it exactly the way they tell you not to do it when you... So if you ever listen to coaches, they always tell you, do your arm the same, and you get the extra power from your legs. You'll hear that if you ever hear a coach talk about three-point shooting. Steph Curry does the exact same amount of leg force, no matter where he shoots on the court. So conventional wisdom is not always right. At least not for superhumans.
How much memory do you have on this?
Too much. You can't buy flash chips with less than 1 gigabyte of memory nowadays. So.
Can you learn all those parameters that you set, the angle and the margin that you give, by using reinforcements from the loop?
Yeah, we can. We can learn that. We can even learn without the hoop, because honestly, the mechanics of how you should do it is somewhat orthogonal if you make or miss it. We'd rather have you miss it with good biomechanics than make it with bad form. If you especially look at youth will spend a lot of time trying to make a basket. honestly, if they're too weak for the distance they're throwing, they're actually they're actually building really, really, really bad biomechanics to get results they want. And so we're actually trying to steer people away from that, which is one of the reasons we don't highlight makes or misses. Because honestly, if you make or miss it is important, but honestly, we'd rather you had good mechanics. We want to make it so that people celebrate good biomechanics, not only good results. Especially important for youth market.
Any roadmap in terms of the types of sports that you're going to support?
Yeah, but not that I'll allow them to talk about. We have other products that we're piloting, both in sports and in other areas. You can imagine what they are. I mean, one of the problems we have is we can do anything. Once you have a biomechanical model, every sport, every domain opens up. So we've been trying to work through which partners we want to go with to produce solutions.
So long term, the data that your company holds probably would be more valuable than any of the hardware that you have, right?
One of the cool things is that we're building a huge database of how people actually move. It's just really fascinating, especially when we start looking at physical therapy. And honestly, spending time in physical therapy, you realize that how little quantitative data there is in physical therapy. It's like the black hole of quantitative study. They like, yeah, that looks good. That's good range of motion. So one of the things we're building is a very deep database of biomechanics of both healthy and unhealthy human bodies.
So would it be safe to assume that it will be a subscription model as you expand your business, right?
Yes. Ideally, the hardware gets cheaper and cheaper. Ideally, we don't even make hardware. I don't want it. The hardware is not the interesting part. It's really the algorithms and the data that's interesting.
It's kind of like the Kindle analogy, real valuable part of the books, the devices, throw away. So that's where you're headed.
That's where we're headed, and we're making hardware until someone else can give me a data stream that's good enough, I will make hardware. The minute I can go take 2 or 3 other people's wearables and cobble them together to give me a good enough data stream, I will drop building my own because it's a hassle to build hardware. It's fascinating. I mean, and as an electrical engineer, you kind of, there's a little bit of pride in, I built this circuit board and I went and did the stupid FCC certification process and I even pay my tax to Underwriter Labs. And yeah, that's a little bit of me as a hardware engineer, so I like that. But honestly, it's really just a hassle that you try to get out of as quick as you can in the business world.
Do you need UL certification for something this low power?
Yes. We do a UL safety certification. It's fairly minor, but we figured in the domain of wearables, because it's on the human body, even though they do.
You look at things like stability, like walking and
Stability and gait's very big, especially in the senior domain.
Yes.
And mobility. It's definitely an interesting area. It's a real challenging one.
Yes. That's what I'm asking.
Predominantly because we've been looking how to measure it. The problem is, how do you get it on the body of your target customer? And the challenge is really in how do you get the sensors where you need them on the body in a real world situation. Whereas if you look at post-acute care, it's much simpler. If someone's going through rehab, it's much easier than trying to put it in a long-term case for just a general population.
I can imagine the biomechanics that you're going through all the time and how you can generate your database with respect to healthy and sport and excellent. But I can also imagine the anthropologist wanting to put your sensors on hard, bony surfaces and things versus soft body tissue parts that you're doing right now. Do you find any on the professional people wanting you to do something different than you're doing right in your demonstration? Like I see the sensors that you have on your arm right now, but
Yeah.
somebody else may want to put them on your elbow and put them on your wrist bone and stuff like that, but if you put them on soft tissue, they move around.
They do move around. What we're trying to do, we're trying to look for spots on the body where there is there's trade-offs. You got a whole set of trade-offs between one, actually where I'm placed here is more optimal for viewing than it is for motion. Back down is fairly good. I don't have a lot of muscle there. I put it up near the wrist where there's not a lot of muscle. Back of the hand is fairly good. I don't want it on the wrist because modeling the wrist, what I want to do is actually see the motion of the hand in space and the forearm in space, and then model the wrist. Biceps are a terrible place to put it, but I can see it really well. So those are the trade-offs that you deal with.
That's just for the show part.
Exactly.
Well, you could always put the LED one place and the sensor somewhere else.
We can, and we also, one of the things we realize is no one ever puts it on right. So a lot of what we do algorithmically is try to deal with the fact that every time you put it on, it's actually going to be slightly different. So a lot of our algorithms are actually trying to deal with the fact that people can't repeatedly put clothes on the same way.
Where are your sensors in there with respect to those lights?
Where you see the lights are where the sensors are in this case. They don't need to be the same, but in this case they are.
So you need to put the Velcro on the person instead of on the sleeve.
Adhesives are really the best way to do it if you really want to know. If you can actually just apply you can actually do just a peel off adhesive and stick the sensors to the human body. That's the best way to do it. It solves a lot of our problems, and we are looking at solutions that may be adhesive based. It actually works real well.
There's no popular piercings out there, so.
Piercings would be another, but that's hard. Piercings tend to move too. Really, just a little bit of adhesive. There are a lot of good adhesive medical domain that will work for us. The problem becomes then battery life and some other issues when you look at adhesive based. But you could look at post-acute care, actually putting on a patient and leaving them there for 3 or 4 days, for the first 2 weeks of care. So it's quite good to stick them on the person.
The EKG guys got that down. I don't know how long it lasts.
Yeah, the gels they use are really good, and those are all certified for medical use, so they're safe to use, and so they have really good materials.
Good. I think we're out of time.
Since you're from Wisconsin visiting Stanford, one of the things that you should do before you go back, Mike Flynn in the computer architecture realm will tell you to do this too. Go over to the Red Barn at Stanford. We have state monuments here to the first work that was done by Muybridge.
Yeah.
Yeah.
So
I actually live here now. I am a Badger. I'm a Badger at heart, but I do live actually in the area now.
Oh, okay.
So yeah, that's the next question. Horse racing.
Horse racing. Horses, we've actually, it's very fascinating.